All right, so the end of chapter 2, capacitors, all of chapter 3, and then the beginning of chapter 4 up till household circuits and RC circuits. So we're not seeing that at all in the exam. No particular questions or topics that you want to look at, Michaela?
Okay. Number 18 on page 2060, that graph that is voltage versus time for a charging capacitor. Do we have that?
No. So, yeah, that's in the RC circuit part of the exam. We won't see that. So anytime you see an exponential and e to the whatever, that's not for you. We're going to get to that later. Multi-loop circuits. Yeah, we didn't really do that very much today, but that is going to be 3 questions on your 3 response. It'll be the first. I think it's the first question, and then also there'll be parts of it in the multiple choice. Let's just do this one right here. So this is number 17 on spring 19. It's a multiple choice question, but we'll do it, like we'll actually calculate the currents, because it's, no, that's not a very good question. Let's do it, and then we'll do another one that's a little bit easier, or I'll make it a little easier for us to work. So first of all, we want to figure out which equations are correct or not correct. When you get one of these, and you'll see one of these, what you want to do is just look at the first number, and I see that's a 2. That tells me that I start right here because I got a 2. And then I see that it's a negative 2. That means that I'm starting right here and I'm going in that direction, because that's how I get a negative 2, right? When I go from high to low on the battery, it has a negative change in potential. So I get negative 2 going through here, and then I come over here and I get plus 2I2. That's correct. There are a couple of things I'm checking. I'm checking the number right here. I'm checking that the current is correct, and the current is correct right there because I have I2 running through that circuit, through this resistor right here at I2. And I'm checking that the sign is correct. And that sign is correct because I'm going against the current. And then I have a plus 4 right here. But look, I'm missing something. As I come around, I'm missing this resistor. So that one's not right. Okay? Then I go look at the junction rule. I just pick any junction, doesn't matter which one. I have I1 coming in, and I2 and I3 going out. So it should be I1 equals I2 plus I3. That's not what that one says, so that's not right. Then the third one is 2. So I'm starting here, and I'm going in this direction, because that gives me positive 2. 2 minus I1. That's okay so far. It's negative, it's I1, and it has a 1 coefficient. That's for the resistor. Minus 2I3. Okay, that looks good because I'm going with the current, so it's negative. And then I come back, and that's everything in. So that must be the answer right there. That is the answer. But let's go ahead and check these other ones. You can see sort of how this works. 2 minus 1I1. So again, here, minus 1I1. So far, so good. Minus 4. That's right. Minus 2.
Minus 1I2, but you said...
Oh, yeah. See? Right, this should be I1 right here, not I2. Those are tricky, aren't they?
So that would be wrong, right?
Yeah, C is not the right answer. That's why it's a good idea to just check them all to make sure. So, like, I would have caught this because I would have seen that, hey, this one is actually right, and then you go back and check C, and you say, okay, well, I made a mistake there. Well, let's check this last one. Y'all saw how D was right? Okay. Just a second, Ben, let me do this last one. So 4, I'm starting here and going this way to get positive 4, and then I get minus 2I2. Okay, this is sort of wonky. Really, like if I started back here, it would be minus 2I2 plus 4, and then that would be minus 2I3. You'll see how this equation actually, if I were to write it, would be 2I2 plus 4 minus 2I3 equals 0. And that's not what I have here. I have something different right here. It's off by a negative sign. I could make this one correct by making this positive and making that negative. Ben.
Only for resistors, or do they work for capacitors?
You know, so far, what we're looking at for capacitors, there is no current in those capacitor circuits. I know that we talk about that there's current flowing, and there is current flowing, but when we have a capacitor that's fully charged, there's no current flowing in that. We'll talk about that when we get back from the test. So, no, Kirchhoff's laws do not work for capacitors, but we haven't talked about any current in capacitor circuits yet. We won't see any current until next week, or later this week. Okay? All right, now let's imagine this circuit. Let's do it as a free response. I would make it a little bit easier in a couple of ways. Either I could give you one of the currents, or I could take out one of the resistors. I'm going to imagine that this resistor is just not there. So no resistor right there. So this is not like one we've seen before, because just made it up. I want to know what is I1, what is I2, and what is I3. Now in your free response, I'm not going to give you the direction. So you're just going to pick a direction. I'm going to pick the directions that are given here. So I have down, up, up. Doesn't matter what direction you pick, okay? Up, 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 down, 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 up, down, down. It doesn't matter. You just pick a direction, whatever, I don't know, floats your boat, as they say. And then I want to figure out what is I1, I2, and I3. I can be clever if I pick my currents right. Actually, here, the best way to do this are to pick, well, which loops am I going to pick? I have big left and right. Which ones will I write equations for? It does matter. Your math gets a little easier if you choose them correctly. The right is one of them. What's the other? You need two equations to solve for two unknowns. And the left. I'm going to pick the right and the left. The reason I knew not to pick the big loop, because if I write an equation for the big loop, it's going to have two unknowns in it, right? It's going to have I1 and it's going to have I3 in it. But if I write this equation, we'll see that it only has I3. If I write this one, it only has I1. Okay? So let's write these equations. I'm going to start here. I get 2 minus 1 I1 minus 4 equals 0. I'm going to hold my pen. I'm going to go ahead and solve this for I1. I get I1 equals negative 2. Negative 2. Okay, and then I'm going to write an equation for the right loop. Let's start right here, and I'll go down in that direction. That's going to be 4 minus 2I3. Sorry, my pen is not working right for some reason. That's equal to 0, so I3 is equal to 2, right? That's right. So now I have I1 is equal to negative 2. That means I1 negative 2. So if I were to write that, I would say it's 2 amps up. That's I1. Because I had chosen it down. It came out negative, so I'll do it up. I3 was 2 amps. That's 2 amps up. It came out positive, so I use the direction that's there. And then if I want to know the third current, I'm going to use the junction rule, which you will want to know that current. I'll just pick a junction. I1 is coming in. I2 and I3 are going out. I1 equals I2 plus I3. And that's equal to I1 is negative 2. I2 I want to know. And then I3 is equal to 2. So that's I2 is negative 4. Okay, so that means that I chose I2 up. That means I2 is going to be 4 amps down. That's going to be very much like your free response. Okay? Yeah, let me just say too that number 15, somebody asked about 15. This little thing right here is kind of wonky. That little wire, it makes it a little bit more complicated. You won't see one like that. Or if you did see one like this problem, it would be such that this wire would not be there. In which case, let me just show you what that would look like while we're here. It would look like I'd have a 2 ohm, a 6 ohm, a 2, and a 3 ohm, and then a 2 and a 6 ohm. It would be 2, 6, 2, 3, 2, 6. I would not have this little wire right there. Okay? And then you could find the equivalent resistance. Which one did you say?
Number 18.
Number 18. This one right here? Okay. Yeah, I guess we did this. I don't know when we did this. We do it in class today? Okay, well, let's look at it again. Because you are going to have a question like it. Yeah, so this, if you see one like this, there's another one, or there are a couple others in other exams where it's similar, except there are no resistors and batteries. Doesn't matter, they're the same problem. But the point is here that my incoming current is equal to the outgoing current. And you can examine each junction to figure out what are the currents that you don't know. So I'm looking for this current right here, I2. Now, if I can know all the currents for this junction, that is, I have a current I3 coming into that junction, I have a current 6 amps going out. If I knew what I3 was, then I could figure out what I2 was, right? Well, shoot, can I figure out what I3 is? I go back in the circuit a little bit, and I look at this junction, and it turns out I can figure out what I3 is, because I have 3 amps going in, 8 amps going in. That means that I3 is equal to 11 amps. You see these two currents right here, this 3 and this 8, come together here to form 11 amps, and then that 11 amps is I3. This I3 comes up, I get 6 amps so that are diverted, so I2 then is 5 amps. That's right. So not worry about the resistors. I don't give any values there. We'll look at another one that's a little more difficult in a more recent exam, okay? Can we look at that one? All right. This was. Maybe that's 21. Yeah, here we go. We did this one too, I think, in class. Well, let's just look at it, because this one, I think we did it today. Yours will be very similar to this. So I'm looking for this current right here. There are 2 junctions on either side of that current, here and here. These 2 pieces, if I could figure out what those 2 pieces are, I could figure out that current, but there's just really not much information. So I'm going to look on the other side. If I can figure out this current right here, then I can figure out this current. And this is the one that I want to know. But I don't know this right off. However, I do see that I have 12 amps coming in and 4 amps going out. That means that whatever is left over, 8 amps, has to be in that wire. And then this 8 amps diverts into a 5 amp, and then this is the current I want to know, which is going to be 3 amps. Okay? So look for those junctions and look for the currents that are missing. And you're going to have to backtrack a little bit, probably one junction back, in order to find the missing current, to find the current that you need. Is that clear?
Yeah, I understood this. With the resistor, I guess I was trying to do something with the resistor.
Oh yeah, don't worry about the resistors. Yeah, you might have resistors on yours, but if there are no values, I don't give any batteries, there's no loop rule that you could write, you just don't have the information for that. Can you hold for just a second? I'm having firewood delivered to my house. I just want to make sure that. You know, hold on, I text them back. Is that okay? Are you taking a picture of my help session?
No,
Sorry.
why look at it?
No, I'm good. Okay, sorry, y'all. We ran out of firewood. It's a terrible thing to run out of firewood, especially we got some cold. Like, we don't have a fireplace in our house, but we have a big fire pit out back, so. I know, we can't miss that, huh? Okay, what else? Let's look at number 18 while we're here, because students sometimes have trouble with this. You're probably going to have one like this, where I give you a voltage on one of the batteries, or a current, not on one of the batteries, on one of the resistors, or a current on one of the resistors. I could do either. And then you have to figure out what is the voltage of the battery. Listen, when you get to these, what you want to do is to figure out what is the equivalent. So I can redraw this as a 2 and a 1 ohm. A 3 and a 6 in parallel is 2 ohms. And then I have 1 ohm right here. Now, if I have 6 volts right here, that means that I have, you know, a current of 6 amps. And if I have 6 amps, that means I also have a current of 6 amps here, which means I have 12 volts across that resistor. But I could have also said this 1 ohm resistor has 6 volts. The 2 ohm resistor has to have twice that. So if I have 12 volts across that and 6 volts across the 1 ohm, then that means that I have 18 volts across the battery, right? Because they add up to give me the total voltage. All right. Yeah. Go ahead.
So, some of the questions that talk about the different sizes of the copper wires,
Oh, yeah.
when do we have to use the equation for area, and when do we not?
So if I give you the radius, then you need to use the equation for area, or the diameter. Either the diameter or the radius works the same. But if I give you the area, then you just use the R equals rho L over A. Like, let's look at this number 13. So, see, notice that I give you the diameter, but here it has area in the equation. So I could just replace that with diameter squared. I'm not even going to write the pi and the over 2. All I'm really concerned about is the diameter squared, because I'm only concerned with the relationship, not the actual value. You see what I did there? I just replaced the area with radius or diameter squared. Okay, you understand why I did that? Pi r squared is our area. So here, if I have a diameter of wire A that's twice as big, that means I have a resistance that's 1/4. I also like to just do a quick check on this to make sure I'm getting it in the right direction. Is it 1/4 or is it 4 times? That if wire A has a bigger diameter, that means it has a smaller resistance, right? It's like the big straw at Sonic. You get a bigger straw, there's less resistance to the milkshake. Have you ever tried to have a milkshake with those little bitty straws? Like, they ran out of the big straws a few months ago or a year ago or whatever. No. Okay, but anyway, if I have a bigger resistor, there's less resistance. So it is correct then that my resistance of wire A is going to be smaller. Well, the answer to your question is, if I give you the area, it's just an inverse linear relationship. But if I give you the radius or the diameter, it's an inverse quadratic relationship. Okay? Of course, you're probably going to see one of those, see them on every test. So, probably going to see one like number 14. You'll certainly see one like number 12.
Question about the one like number 12. On number 10 on, I think it's 2016, the answer ended up being 1 times 10 to the negative 7, but the right answer was 10 times 10 to the negative 8. Are we going to see, like, will it be like switch like that where we're going to have to, like, figure out and see which ones are the same, or is it going to be like that?
Yeah, this number 10. Yeah, that's possible. But, I mean, you know, I know that you know,
No.
that this is the same as 1 times 10 to the minus 7, right? So, yeah, you could see that. And also, if you calculated that, you could just look at this number. Is that number, is it called the mantissa? I think it is. I should know that. Anyway, you can just look at that preceding number, and since there are no 1s, then iron is the only appropriate one. Okay, is that clear? I see how that's confusing. I'm sorry. The reason that they have that in the table is so that every one of them has 10 to the minus 8. That's why. Ben?
What term is resistivity in a metal?
The resistivity is just dependent upon the metal itself. So, you know, how many valence electrons does it have, and how freely can they move, right? So wood, for example, has a very, very, very big resistivity because it's a good insulator. Wayne?
Can we look at some of the concept ones that's talking about like the light bulbs or the biggest?
Oh, yeah. Yeah. Or rank these. I like ranking problems, don't you?
No, they have a ranking one about wires somewhere.
Yeah, we do. Yeah.
Yeah, there's one right here. Let me do this ranking one right quick. What do you mean no? Who said no? Okay, so 5 cylindrical wires are made of the same material. Their lengths and radii are given like this. Rank the wires according to their resistances. Well, first of all, you know, R is equal to rho L over A. R, I could say, R is equal to rho L over R squared. That's the radius squared. And so I'm looking for the biggest one. The biggest one is going to be the one with the longest length and the smallest radius. So that would be, what, wire 4? No, I'm going least to greatest. The one with the least resistance is the shortest one with the biggest radius. So, well, I don't have a good one. Let's just figure out what is the coefficient for each of these. So, for example, here, for wire number 1, I have a 1 for length, and I have a 1 for radius. So I just have a 1 right here. 1 over 1 squared. Goodness bless you. For the second one, for the length, I have a 1 over 4. See, that's what I got right there, 1 over 4. You'll see what I did? And I have a radius of 1 over 2. So that means I have 1 over 2 squared is 1/4. So this is just 1. Oh, look, now I know that wire 1 is equal to wire 2. So I can just go ahead and say that's the answer. But let's go ahead and check these last ones. So for F over 2, that was the length. So I have a 1 over 2. And then for the radius, I have a 1 over 2 as well. So that's a 4 over 2, or 2. Yeah? Because area is equal to pi r squared. I just left it off. It's just a number. So you can put the pi in there if you want. Okay? For wire 4, this. For wire 4, I have a 1 right here for right there. And then I have a 1 over 2 squared. So that's equal to 4. And then wire 5, I have a 5 up here and a 2 down here, so that's 5 over 4. So I'm going from least to greatest. 1 is equal to 2. Next is 5, then 3, and then 4. Because 5 over 4 is 1 1/4. Okay? Follow? Okay. But we weren't really looking for that. We were looking for the light bulb problems, right? You don't know what number or where that would be exactly? Oh yeah, okay. So consider these three circuits. Which provides the most light? First thing you need to recognize that C is just two light bulbs in parallel. So C is the same as that circuit. You see how that's the same circuit? You see? See? If I come here, I break into a junction. Right here, I break into a junction that goes into that resistor and that resistor, which it does here, and then it comes back. So if you can see this, it'll really help you with those capacitor circuits. If you can see how this circuit is the same as this circuit, let me show you again. So as I come along here, I come to a junction right here. Notice how I do this. I come along here and I come to a junction. And then this junction splits into two. I split into two right here. In those two parts, I go through the resistors. Right there. Come back here, and then I go back to the battery. Seeing this will really help you, because that's sort of what you have to do with those capacitor circuits, is be able to follow through and see where those junctions take you. Some people are really good at this, and some people have to work at it to get good at it. But all of you can be good at it. There's no doubt about that. But some people, they see things more spatially. My wife is sort of that way. All right. So then, which one provides the most light? Let's imagine that I have, say, 2 volts on each of these. Doesn't matter, but if I have 2 volts on each of these, on this light bulb, or on these two, they're going to split up that voltage. So I get 1 volt and 1 volt. On this one, I'm going to get 2 volts. And then on this one, because they're in parallel, I'm going to get 2 volts on both of them. Okay, so the one that provides the most light is which one, A, B, or C? C, right, because I have 2 light bulbs, each of them with 2 volts. And then the next one will be B, and then the least dim will be A. Remember, too, that when I say brightness, I'm talking about power. And power is equal to V squared over R. That the resistances are all the same, so it's dependent upon the voltage. And notice that power is more heavily dependent upon voltage. If my voltage goes up by a factor of 2, my power goes up by a factor of 4. Okay? So, in saying that, this light bulb puts out more light than both of these combined. Because the power put out by this one would be 4 times P, and each of these would add 1 times P. So these combined would give you 2 power, and this would give you 4 power. Okay? Alright, let's try this other one. Which of these statements is correct? Bulb A is twice as bright. Well, let's just think about the voltages first. So again, we'll say 2 volts and 2 volts. Just picking a number. I pick that number because it divides easily by 2. So I get 1 volt here and 1 volt here, and I get 2 volts here. Remembering, for power, that it's equal to V squared over R. The reason, by the way, I didn't use this expression, P equal VI, is because for these light bulbs, they have different voltages, and they have different currents. And I don't really know right off what the currents are, but I do know right off what the voltages are. However, they all have the same resistance, but they have different voltages. So I'm picking an equation where I just have one variable that's changing. Okay? So bulb A is twice as bright as bulb B. Not true. They are both the same brightness. Bulb A is 1/4 as bright as bulb C. Well, bulb A is has half the voltage, so it is 1/4 the power. So it looks like B is right. Let's just step through these other ones. Bulb A is 4 times brighter than bulb C. Not true. Less voltage. It's not going to have as much power. Bulb A is 1/2. It has half the voltage, but not half the power because it's dependent upon V squared. And then bulb A is twice as bright as bulb C. No, that's not true either because it's less bright. Okay? I like those kinds of questions. Questions that don't have numbers that you have to think more about them, I think. All right? Sure. I like these questions too. I like non-numbered questions. And if you're pre-med, MCAT does too. Like they like these non-calculation questions because you can't use a calculator, right? They try to make it easier for you because they're so nice. So hey Brooks. Yeah, so which has the biggest current? Well, look, I have R, 2, 3, 4, 5, and 6. Which of these resistors actually does have the biggest current? R1, right. All the current comes off this battery and goes through this resistor. Okay, but that's not listed in these options, so I have to pick one of these others. So this current, I have to figure out where does most of the current go. I have 6 ohms up here, and I have 3 ohms down here. Do y'all see how I got that 3 ohms? I have a 3 and 6 in parallel. That's 2 ohms in series with 1 ohm, so it's 3 ohms. Now, most of the current, or more of the current, is going to go through the path with least resistance. In fact, I'm going to get twice as much current here than I get here, because I have half the resistance. Now, I have less resistance, I get more current. So, I can get rid of these two. Now, that current, because I get less current in that top branch. That current also is going to be split when it goes through these two resistors. So it's not going to be either of those resistors. It's going to be R6 will have the most current. Really, R1 has the most current, but then the next biggest is going to be R6. Reagan?
So if the top had 3 and the bottom was 6, would the answer be one of the top 2?
Yeah, so if this was 3 and this was 6 and I was looking for the biggest current, it would be one of the top 2. It would be both. They both have the same current. So if that was the case, for example, if that was the case, I either wouldn't list R2 or R3 in the options. It would be one of those. That's good thinking because, on these questions, often I'll just pick a question that I've given before. I also give you a different circuit. Same question, I just give you a different circuit. So it's still testing the same skills. So it's good to think that way when you're practicing these old tests, is how would he change this question in order to make it a new question? That's how I do the final too, right? So, all right? Good. What else? Yeah, the capacitor. Yeah, people freak out over that, don't they? Look, here's one. We haven't done this one yet. Spring 20. Yeah, spring 20. Okay, so I'm going to start at the high side of the 12-volt battery. I'm going to redraw it. So redraw your 12-volt battery over here somewhere. I'm going to come up. Remember, this isn't a junction. This is a pin, not a junction. A junction splits into two or more wires. And then I'm going to go through this capacitor. And then over here, I'm going to split into a parallel branch, and it's going to have how many parts to it? It's going to have 2. And then notice that they all come back together right here. And then it splits again into 2. And then these go through, and they come back here, and they go back to the battery.
I'm following until you get to C36 and
All right, let's just draw up to that point. I'm not going to draw it. I'm going to draw that half of the circuit, and then we'll talk about it. So here's my C6. This is C4 and C5. They come back together, and then something else happens. So this is where they come back together. Okay? You'll see how these wires, they come back together at this point? That's this point right here. But then, notice they split up again. And one of those branches has just the 1 microfarad, and then the other has these two. So what does this part of the circuit look like? How many branches does it have first? It has 2. And which are in the first of those branches? Just C3. And then what about the other? Are they in series? These two capacitors? They are in series. Huh? Right, these are just bins. There's no junctions between them. So these two capacitors are in series. I could take this capacitor and move it all the way over here, and that wouldn't change the circuit. So then I break into 2 capacitors again, or 2 branches again. This is C2. This is, oh, not C2, C3, excuse me. And then C2 and C1. And then this goes back to the battery. All right, now when we do it, is that okay? This is 2 microfarads, 2 and 4 microfarads, 1, 4, and 4. So 2, this is going to be what? 6 is right, they're in parallel, so I just add them up, 2 plus 4. Here I have a 4 and 4 in series. 2, 1 over a quarter plus a quarter, that's equal to a half. 1 over a half is equal to 2. And then I have 1. So I have a 2, 6, and 3. Right. So I have 2, 6, and 3. That's right. Yep. So I have my battery. Two, 6, and 3. And then I find the equivalent of that, I forget what this is, 1 over, or 3 6, that's a half, plus 1 over 6, plus 2 over 6, that's 1 over 3, oh, that's 1. All right, so these are all equal to 1. 1 microfarad, yeah, Ben?
Could you break it up again into 6 and 3 and maybe 2 and 2?
Oh, I didn't do that. What now?
Could you take a 6 and a 3 and combine it into 2 and 2 and 1?
Oh, yeah, you could do that.
That's how I do that.
Really?
I put the other one.
Oh, yeah, that's clever. Yeah, that's good. I like that. Y'all see what they did? What property is that? Is that the commutative property of addition? Is that right? I'll read it. Yeah, so what they did is because they know a 6 and 3 in series is 2, they just make that into a 2, and then they combine the 2 with the 2 to get 1. That's clever, y'all. But you can do it in your head, right? You don't have to go over and do it. I like that. All right, so now that I get this circuit, I have a 12 volt and a 1 microfarad capacitor. I know that it has 12 microcoulombs. So I have 12 microcoulombs here, 12 microcoulombs here, and 12 microcoulombs here. Then I can figure out the voltages. The voltage is equal to Q divided by C. Now see what I did here? I found the charge here. Q is equal to C times V. 1 times 12 is 12. Capacitors in series have the same charge. So I have the charge here, all the same. And they're all the same as the equivalent. Now I can figure out the voltage, which is going to be 12 divided by 2, or 6 volts. 12 divided by 6 are 2 volts, and 12 divided by 3 are 4 volts. I'm going to do a quick check, make sure I got it right. 6 plus 2 plus 4 is equal to 12, and that's what it should equal. Also, I noticed that my big capacitor, or my small capacitor has the biggest voltage, and my biggest capacitor has the smallest voltage. That's how they should be for capacitors. Now that I have that, I can come back up here and start labeling some of these. This one is 6 volts. I just carried that over. These are both 2 volts because they're in parallel. And so they share the same voltage as this capacitor right here. This has 4 volts. These combined have 4 volts, but they split it. They're identical, so they're going to have 2 volts and 2 volts. Oh, that's a 2. So then, I can just go and, well, my equivalent was 1. My voltage on C2, which is this, which one is that? Oh yeah, so it's right here. So that's 2 volts. And then to find the energy on C4, that's 1/2 CV squared. And you just plug in the numbers for C and B. Okay? I don't know if there are any energy questions. I don't remember putting them on there. It's easy though, right? You have the equations. If it is, don't worry about trying to memorize the equation. Just look on your equation sheet. I don't think there are any on there.
Is 1/2 CV squared?
That should be a C. My pen is not. It has a lag. It is 1/2 CV squared and 1/2. I don't remember. They're on the equation sheet though. Those expressions for energy. But yeah, I'm pretty sure I didn't put any on there. Don't hold me to that, but I'm pretty sure I did. Okay? What else, y'all?
And the concept ones where it's like if you take away a resistor, what happens to the other one?
Oh yeah, I like those too, don't you? Yes, you do. Right? Thanks, Aaron. Doesn't see one here.
Would the voltage go to the path of least resistance to, like, if there was? No.
When we talk about voltage, we never talk about it going through anything. Like, there is no voltage through anything. There's only voltage across 2 points. So if you ever notice, like when I talk about current, we say, oh, the current goes through the resistor. When we talk about voltage, it's between 2 points. So
The way I remember it is that they have equal access to the battery, so it's gonna have the same.
in parallel, yeah, when it's in parallel. So when it's in parallel, they have the same voltage.
So
Right?
if we were looking at one of the other ones, like the current ones, where we talk about the largest current, would it be like the same idea as largest current?
Yeah, well, if they're in parallel, and they were in those problems that we were working with, they have the same voltage. Both branches have the same voltage. That's how we can say then that if one has a smaller resistance, it gets more current, because the voltages are the same. Okay? Looking for one of those questions. Anybody know where those are?
It's like a rectangle and it had like the line through the middle.
Oh yeah, I'll show you one of those in just a second.
It's something like that gonna be on the test. Or not.
Maybe. I don't remember. I made the test last week. I don't really remember what's on it. It might have optics on it for all I know. Oh wait, no, we're not doing optics yet, are we?
It has like, I don't know what that is.
I'm just joking. 18. Are you talking about this one, Tiffany?
But that's what I was talking about.
Yeah, I know. Okay. If one of the 2 ohm resistors is removed, what happens to the current through the remaining resistor? So remember, with resistors in parallel, the more resistors you have, the less the equivalent resistance. Even if they're really big resistors, if I add more in parallel, it gives more pathways for the electricity to flow, and so it will decrease the resistance. So if I take away a resistor, that means that the resistance has gone up, and if the resistance goes up, the current goes down. So the current here through the remaining resistor would decrease because my overall resistance would increase. Now, the one with the, I think I had it. This one right here, don't be thrown off by this. I could redraw this. I'm drawing between these 2 points. Imagine that there's a battery there. If I redraw it, I'm just breaking into 3 branches. Oh, shoot, sorry. Those are the same circuits. Sorry, my capacitors look more like resistors. My pen was not working right. Oh, oh yeah. Okay, so I'm sorry, I was reading it incorrectly. The overall current goes down, but the current in the resistor remains the same. Y'all see the difference? Yeah, so we're asking this was asking for the current through here. Oh, it makes sense. It does. Because look, if I have a circuit like this, I have a total current that runs through or coming off the battery. But then that current splits into 2 pieces here and here. If I take away this part, then this total current will go down. But the current here will remain the same.
Because 4 volts is going to both of them.
Because I got 4 volts going to both.
Then still go through the same one, but the total current still goes down.
That's right. That's right. I'm sorry, I didn't read it correctly. Let me repeat that. So notice you have 2 currents. You have the total current coming here. As I add resistors in parallel, the total current goes up because I'm adding each individual current to this total circuit right here. Now this voltage stays the same. It's going to stay 4 volts. No matter how many resistors I have out here, I'm still going to have 4 volts. So I will still have 2 amps of current. 4 volts divided by 2 ohms gives me 2 amps of current. So if I take away this resistor, this current will stay the same, but this current will go down. Or if I add resistors, this current will stay the same, but this current will do what? It'll go up, right? Because as I add resistors in parallel, the total current goes up. I total equals I1 plus I2 plus I3 plus I4. That was one of our rules for resistors in parallel.
So how does that change if it's in series then, like?
Oh, if it's in series, yes, it does change. Let's say that we've had similar questions. Say if I have 2 resistors in series, if I remove one of the resistors, that means the overall resistance goes down. That means that the total current goes up. And there is no individual current. There is no current in that resistor because whatever current is here is also in the resistor. Right? Every resistor has the same current, and that's the same as the current of the equivalent resistor, or the total current in that circuit.
Take them away, the resistor goes down.
Yeah, if I take away this resistor, the equivalent resistance goes down. I have less resistance to the flow of electricity, and so my current then is going to go up.
But the current in that one resistor still stays the same?
No, it's going to go up.
Because the current is constant throughout it.
Yeah, the current here is equal to the current here. Resistors in series have the same current. Right? So if I remove one of these, my overall resistance has gone down. So the current will go up because I have the same amount of energy, but I have less resistance to the flow of electricity, so I get more current. And so this resistor would see more current. That's true, yeah. So the voltage would also go up in this resistor. Yeah, that's good. Okay.
Back on the other one. How come the resistance is going up if you're taking away a resistor?
Ah. Yeah, because but with parallel, if I add a resistor, I've added an additional path for the electricity to flow, which decreases the overall resistance. It's sort of like your what's it called? Your arteriole. You know what I'm talking about? Arterioles. They split into the capillaries. They split into a whole bunch of those capillaries. So actually, your overall resistance goes down, even though your capillaries get really small because you have so many capillaries, but your arterioles, which have a low resistance, actually split into.
That just makes sense to me.
Okay, it's the same idea. Okay?
And then you start talking about that, and I got
Biology. Oh, you're on my top. Okay? Is that clear, Reagan? Okay. Is that all, y'all? Yeah, maybe? Yes?
Okay, I have one question.
Okay.
So if you may have said it, but if you add one, the overall will go down, but the individual.
If I add a resistor in parallel, if I add a resistor in parallel, the equivalent resistance goes down. The total current goes up, right? The current here, but the voltage or current in any individual resistor doesn't change, right? This resistor is independent of this one or this one or this one. Okay? Right. Yes. Okay. I think I got her. Elena's the only one that came in a minute or so late, right? I got her right.